Hey everybody, it's Brandon from STEM Tutor Club, and today we're going to go over this exponent property. You can see why it's called the power of a product because we have two values here being multiplied together, which we create a product, and then we're taking them to a certain power. We're going to deconstruct exactly why this works so that we can understand it. But before we get into that, let's try to go over some examples for exactly how we might even use this property. So here, if we have this expression, 3 times 4, that quantity squared, there are two separate ways that we could calculate that, without the property and with the property. So first, going without the property, we can just directly use the order of operations. So PEMDAS, parentheses comes first, so we do whatever's in the parentheses, and then after that we'll do the exponents. So 3 times 4, that'll be 12, and then 12 squared, that'll be 144. That's one way to do it. The second way, using the property over here, would be to apply the power n to x and y. So in this case, we can specify that x would be equal to 3, y would be equal to 4, and then n would be equal to 2. And then whatever we see on the left side, you can see that you can check that that works out because we get 3 times 4 raised to the power 2, which is the expression that we're trying to calculate. And then all we have to do is substitute in the right side of this equation with these values set to these numbers. So for example, x raised to the power n, that would be 3 squared. And then y raised to the power n, that would be 4 squared. And this property sort of looks like we're distributing the exponent into each factor. That's not exactly what's happening, but you can think of it that way. That is a good way to remember it. So if we calculate this, 3 squared, what would that be? That'll be 9. And 4 squared, what is that? 16. So 9 times 16. Well, we could calculate this. So if we do 16 times 9 just by hand, so 9 times 6 is 54. So 4 carry 5. 9 times 1 is 9, plus 5 is 1, 4. So you see we get 144 this way as well. So we get the same answer both ways, just to show you an example of how this property can be used to get the answer that we expect. However, what you might be asking yourself is, why would we ever use this property? The way we calculated it without the property was much faster. And that's true. If you know all the numbers, you should not use this property. This property should really only be used for cases where you have something like this. So if we had, for example, 6x and the entire thing raised to the second power, well, here we don't know what x is. In other words, we have an unknown. So there it actually makes sense to use the property to simplify it as much as possible. So we would distribute the exponent, if you want to think of it like that. So 6 squared times x squared, and 6 squared is 36. So 36x squared would be the simplest that we could make this expression, given that we don't know what x actually is. And this is the real use case for this property. Now I want to get into exactly why that worked, why we were able to calculate it with the property as well. And as with all exponent properties, the best way to understand why this works is to expand out the exponent. So if we have 3 to the fourth power squared, what is that? That means the definition of squaring, or raising to the second power, means that we multiply whatever's being squared, in this case everything in parentheses, by itself twice. So if we do that, if we write that out, we get 3 times 4. That's it being multiplied by itself once, and then we're going to multiply it by itself again. And then here, because of the associative and commutative properties of multiplication, we can rearrange these. So in other words, we can choose to represent this as 3 times 3. In other words, we can group the two 3's together, and then we can also group the two 4's together. And then if you think about this, by definition, 3 times 3 is equal to 3 squared, and then 4 times 4 is equal to 4 squared. So you can see that we get this property for these specific numbers at the end when we choose to look at it this way. And if we wanted to generalize the work we just did to apply to any values of x, y, and n, which is similar to a proof that you would see in a textbook, we can do something like this. So x times y raised to the power n, we could represent that as x times y times x times y. And we don't know how many times we're going to be doing this because we don't know what n is here. But generally what we could do is we could represent this with n. We could just say that we're multiplying n of these terms, or n of these factors. I'll just say n times, that might be easier. And then what we can do is rearrange it to have all the x's together. So x times x times however many times. So we might have n times here. So n times, and then we could do the same thing with the y. So in other words, just the commutative and associative properties of multiplication. You can move around numbers to wherever you want, and you can group them together however you want. So if we do that, you can see that we would end up with something like this. And then according to the definition of exponents, x times itself, n times, is equal to x raised to the nth power. And then y times itself, n times, is equal to y to the nth power. So this is the more general proof for how this formula works. And finally, just to wrap up, I wanted to make a couple comments. This property can actually be generalized to no matter how many factors you have being multiplied together inside of the parentheses, no matter how many you have, the property is easily generalized. So for example, if we have x times y times z, so in other words, we're throwing in the z to our multiplication now, not just x and y, well, then we would just have another term on the other side times z to the n power. Again, just thinking of it loosely, we can distribute the power to each factor, even though that's not technically what's going on. You can think of it that way. And then same thing with 4. If we have 4 variables a, b, c, d, we can do the same thing. We would just have 4. You could do it with 10 or 100 or however many variables you have. If you have all of them multiplied together and then raised to a certain power, you could basically switch the order. You could raise them all to the power first and then multiply them afterwards. So I hope this video has made this exponent property make more sense for you, and be sure to stick around for the other exponent properties that we're going to go over in subsequent videos. See you then.